Hello everyone, I am BSSP Rajashekhar, Assistant Professor of Mathematics, Government Degree College for Women, Nalgonda. This is the second class on vector spaces. In this class, first let us quickly recap the vector space definition and some properties of vector spaces which we have proved in the previous class, and we do some examples in this class. R power n, we call it as Rn, is a vector space, and the set Pn of polynomials of degree at most n is a vector space, and other examples are vector spaces. This is the today's class map. First, let us recap the definition of vector space. A vector space is a non-empty set V of objects called vectors on which two operations called addition and multiplication by scalars are defined with the following axioms. So vector space is a non-empty set with some properties, with 10 properties on vector addition and multiplication. Those 10 properties are listed here. U plus V belongs to V, that is closure property with respect to vector addition, and this is comparative property with respect to vector addition. U plus V is equal to V plus U, and this is third one is associativity. U plus V plus W is equal to U plus V plus W, and there must be a zero vector O in V such that U plus O is equal to U. For each vector U in V, there is a vector minus U called negative of U in V such that U plus minus U is equal to 0. Minus U is equal to O. We are calling it as O, the zero vector. So these 5 axioms are related to vector addition. And now the scalar multiple of U by C denoted by Cu is in V. That is, Cu belongs to V. This closure property with respect to scalar multiplication. And C times U plus V is equal to Cu plus Cv, vector distribution.
And C plus D times U is equal to Cu plus Du. Here C and D are scalars and U is a vector. And the ninth one is C times Du is equal to Cd times U. Finally, 1U is equal to U. If a non-empty set satisfies all these 10 conditions, we say that that set is a vector space.
There must be only one zero vector in each vector space. And the second one is the negative for each vector U is also unique in a vector space. You can't get two negatives for a single vector. Negatives must also be unique. And later we'll prove some of the properties. That is OU is equal to O, 0U is equal to O for every U belongs to V. 0 is the scalar. If you multiply any vector of the vector space with 0, you will get the zero vector of the space. That is the first property. And CO is equal to O, where O is the zero vector. It holds for every scalar C. And minus 1 times U is equal to minus U. Here minus 1 is the multiplicative inverse of the identity. And finally, we have proved that suppose Cu is equal to O for some non-zero scalar C, then U must be a zero vector. This is what we have seen in the previous class. Today, in our class, we are going to discuss about some of the examples. Let us prove how to prove a vector space. Let us first take the space Rn. The space is Rn where n greater than or equal to 1 are vector spaces. This is what we are going to prove now. We know what is R. R is a set of real numbers. And here we are defining Rn. For convenience, let us name it as V. Let V is equal to Rn is equal to set of n tuples, that is A1, A2 and so on An, such that each AI belongs to R. I is equal to 1, 2 and so on up to n. So in a vector space V, in the set V, which is Rn here, it is a set of n tuples where each element each element of n tuple is a real number. We can also denote it by a matrix, by a column matrix, n by 1 column matrix. But for convenience, we are writing in this notation. So this is our Rn. Let us take two elements of Rn. If alpha is equal to A1, A2 and so on An, and beta is equal to B1, B2 and so on Bn, are two elements of V, and x, y are scalars. I am taking x and y are scalars in this problem. Define addition and scalar multiplication in V is equal to R power n as we need to define two operations on this set so as to show that it is a vector space. First of all, let us define addition, vector addition and scalar multiplication. So alpha plus beta is equal to this n tuple A1, A2 and so on An, plus beta is this n tuple B1, B2 and so on Bn. So this is defined as this one, A1 plus B1, B2 plus B2 and so on An plus B. Component wise addition. You can simply see it in a matrix addition. So this is A1, A2 and so on An. It's a column matrix. This next one is B1, B2 and so on Bn is another column matrix. If you add those two matrices, you will get A1 plus B1 in the first row, A2 plus B2 in the second row, and finally An plus Bn in the final row. So this is component wise addition. We are defining alpha plus beta as this one. And similarly, scalar multiplication x alpha is defined as x times alpha. Alpha means A1, A2 and so on An, that is equal to x is multiplied by each and every component of the vector. So this is xa1, xa2 and so on xa. This can also be seen in matrix multiplication with the scalar. If you multiply C with the matrix, you will get C in each element. So this is scalar multiplication. With these two operations, we are going to show that Rn is a vector space. To show that Rn is a vector space, we need to prove all the 10 axioms. All the 10 axioms. So first one, closure property with respect to vector addition. So for alpha, beta belongs to V, we have alpha plus beta is equal to, this is alpha and this is beta. We have already seen this in the definition of vector addition. So by adding these two as per our definition, we will get this one, A1 plus B1, A2 plus B2 and so on, An plus Bn. So this belongs to V. V is our Rn, since each Ai plus Bi is a real number. Here A1, A2 and so on An are real numbers. B1, B2 and so on Bn are real numbers. You add these two, by adding two real numbers, you will get another real number. So all the components are only real numbers. So it satisfies the condition of Rn. So each and every entry is a real number. That is why it is in Rn. That is denoted by V. So the resultant vector after adding two vectors as per our definition is also in V or vector space. That is why our definition scalar addition is closed. The next commutative property, the second one, for alpha beta belongs to V, we have alpha plus beta is equal to, again alpha is A1, A2 and so on An, and beta is B1, B2 and so on Bn. After adding these two, you will get A1 plus B1, A2 plus B2 and so on Bn plus Bn. That is equal to, you can interchange A1 plus B1 as B1 plus A1. Since these are real numbers, real numbers holds commutative property. So in real numbers, x plus y is equal to y plus x. So I can write this as b1 plus a1 and b2 plus a2 and so on bn plus a1. So that is equal to, this can be written as b1, b2 and so on bn plus a1, a2 and so on a1. This is nothing but beta and this is alpha. So this is beta plus alpha. So finally we got alpha plus beta is equal to beta plus alpha. So commutative property with respect to vector addition holds in P. Now let us move on to the third property, associative property. For alpha, beta, gamma belongs to V, where gamma is equal to, we have already introduced alpha and beta. Gamma is introduced now. Gamma is C1, C2 and so on Cn. Then alpha plus beta plus gamma is equal to, first we have to operate these two vectors, alpha plus beta. So we have already seen the value of alpha plus beta. Alpha plus beta is a1 plus b1, a2 plus b2 and so on an plus bn. So this is the resultant vector of alpha plus beta. This is being added to gamma. Plus gamma is c1, c2 and so on cn. So this is a real number. Alpha plus b1, a1 plus b1 is a real number and c1 is another real number. So adding these two vectors, we get the first component of the resultant vector must be a1 plus b1 plus c1. Similarly, second component of the resultant vector is a2 plus b2, which is a real number that should be added to this c2 and so on. So this is the resultant vector. But in real numbers, associativity holds. So by associativity of real numbers, we can write it as a1 plus b1 plus c1, since these are all real numbers. Similarly, this can be written as a2 plus b2 plus c, and so on. So this can be further written as a1, a2 and so on an plus b1 plus c1 is the first component and b2 plus c2 is the second component and so on bn plus cn. So this is alpha and this is nothing but beta plus gamma. So finally we can conclude that alpha plus beta plus gamma is equal to alpha plus beta plus gamma. So associative property with respect to vector addition holds in our. Now the fourth problem, existence of zero vector. So we have to show that there will be a zero vector in V such that 0 plus alpha is alpha. So the element O is taken as all zeros. So all the components are zeros. So since all the zeros are real numbers, so this element belongs to V, that is Rn. So alpha plus 0 is equal to alpha is A1, A2 and so on An plus 0, 0, 0 and so on. After component wise addition, you will get A1 plus 0, that is A1, A2 plus 0, A2 and so on. An plus 0 is A, that is equal to R. So alpha plus O is alpha. So O is the zero vector. So we find a zero vector in our Rn. That is existence of negative for each vector. So now we need to find a negative for each vector. For alpha belongs to B, there exists minus alpha, that is equal to minus A1, minus A2 and so on minus A. So since A1, A2 and so on An are real numbers, minus A1, minus A2 and minus An are also real numbers. So whenever all the components are real numbers and it is an n-tuple, it belongs to Rn or V. So this belongs to V. Now alpha plus this minus alpha, this is denoted by minus alpha. Alpha plus minus alpha is equal to, or alpha is A1, A2 and so on An, that is added to this vector minus A1, minus A2 and so on minus A1. After component wise addition, A1 plus minus A1, A2 plus minus A2 and so on, An plus minus A1. So A1 and minus A1 are real numbers. A1 minus A1 is 0 and A2 minus A2 is also 0. That's similarly An minus An is also 0. So it is a vector with all zeros, the n-tuple with all zeros. So it is our O, zero vector O, as seen in our previous case. So we find a vector. We find a vector minus alpha for alpha such that alpha plus minus alpha is equal to O, the zero vector. So alpha has a negative and minus alpha is the negative of alpha. Similarly, we can prove that for each vector in V, there must be a negative. So there exists a negative for each vector in V. So these five are the axioms related to vector addition. All are proved now. Let us move on to the axioms related to scalar multiplication. B is closed under scalar multiplication. B is closed under scalar multiplication. So for x belongs to R, let us take a real number x, and alpha belongs to B, it is a n-tuple. X alpha is equal to x times alpha. Alpha is a pair here, A1, A2 and so on here. So this multiplication is defined as component wise multiplication, xa1, xa2 and so on xan in our definition. So since a1, a2 and so on an are real numbers, xa1, xa2 and xan are also real numbers. So it is an n-tuple with all real numbers. So this belongs to Rn, that is. So we can conclude that B is closed under scalar multiplication. So our sixth axiom is also true. Now seventh one. X times alpha plus beta is equal to x alpha plus x beta. So here x is a real number and alpha beta belongs to our set Rn, that is V. X times alpha plus beta is equal to x times alpha plus beta. We have already seen this vector in previous exams. That is a1 plus b1, a2 plus b2, and so on, an plus bn. So by the definition of scalar multiplication, x is to be multiplied with each of these components. So component wise multiplication. So x times a1 plus b1. This is the first component. X times a2 plus b2, and so on. X times an plus b2. This can be distributed since we are in the real. All these are real numbers, and distributive laws holds good in real numbers. You can write it as xa1 plus xb1. This is the first component. Similarly, this is xa2 plus xb2, and so on. Xan plus xbn by distributive laws of real numbers. So this can be separated as xa1, xa2, and xan plus xb1, xb2, and so on, xbn. Further, these vectors can be written as x times a1, a2, and so on, an, and plus x times b1, b2, bn. So a1, a2, an is nothing but alpha, b1, b2, and so on, bn is nothing but beta. So this is equal to x alpha plus x beta. So from this we can conclude that x times alpha plus beta is equal to x alpha plus x beta. So the seventh axiom is also true. Now the eighth one. X plus y times alpha is equal to x alpha plus y alpha. So here x and y are real numbers, the scalars, and alpha is the vector that is in V. So x plus y times alpha is equal to x plus y. Alpha is a1, a2, and so on, an. That is equal to x plus y is a scalar. That scalar is being multiplied by each and every component of the vector. So this is x plus y a1, x plus y a2, and so on, x plus y an. Again, all the three are x, y, a1. All the three are real numbers. So by distributive laws in real numbers, we can write it as x a1 plus y a1. Similarly here, x a2 plus y a2, and so on, x an plus y an. This vector can be written as x a1 plus x a2 plus x, and so on, x an plus y a1, y a2, and so on, y an. This is x alpha, x times a1, a2, and so on, an. That is x alpha. This is y alpha. So you can conclude that x plus y times alpha is equal to x alpha plus y alpha. So we have proved the eighth axiom also. Now let us move on to the ninth axiom. Xy times alpha is equal to x times y alpha. For xy belongs to R and alpha belongs to V, here both x and y are scalars and alpha is the vector. Xy times alpha is equal to xy. Alpha is a1, a2, and so on, an. So after scalar multiplication, you will get xy a1, xy a2, and so on, xy an. This is by the definition of scalar multiplication. This can be written as x times ya1, x times ya2, and so on, x times yan, by using the associative properties of real numbers. So the multiplicative associative property is used here. So in the field of real numbers, this associative law with respect to multiplication also holds. That is why we can write in this manner. So this can be written as x times ya1, ya2, and so on, yan, and it can be written as x times y alpha. This is nothing but y times a1, a2, an, that is alpha, x times y alpha. So we can conclude that xy alpha is equal to x times y alpha. So ninth axiom is also true. Now the finally last one. 1 alpha is equal to alpha. Here 1 is a real number and alpha is a vector in V. So 1 alpha is equal to 1 times a1, a2, and so on. So after multiplying 1 with all the components, we get the same a1, a2, and so on. This is nothing but alpha. So 1 alpha is equal to alpha. So we have proved all the 10 axioms of vector space. So we can conclude that V is equal to Rn or R power n. We simply call it as Rn. Is a vector space. So it is a n tuple where n greater than or equal to 1. So this result can be used for any n, of course, for any positive natural number n. So if you have to prove that R3 is a vector space, you will get a 3 tuples. You will get 3 order triads or 3 tuples. If you want to prove it's R power 5, R5 as vector space, you will get a 5 tuple. And the entire procedure is same. So this Rn is similar to many of the vector spaces. The proof is almost similar to this one. In this proof, we have proved all the 10 axioms thoroughly. In the later part, we can use the concept used here. So let us take another example. The set Pn of polynomials of degree at most n is a vector space. So polynomials are my vectors here. For n greater than or equal to 0, the set Pn of polynomials of degree at most n consists of all polynomials of the form. So each vector of our set will be of the form P of P is equal to a0 plus a1t plus a2t square and so on an p power n, where the coefficients a0 and so on an and the variable t are real numbers. So here all the coefficients are real numbers and the variable t is also real number. So this problem is almost similar to the previous one. Of course, here we have n plus 1 terms. If you list all these a0, a1, a2, and an, there will be n plus 1 terms. So it is almost similar to the previous one. First of all, we need to define zero element and other things. The degree of p is the highest power. In this definition, the degree of p is the highest power of p whose coefficient of is non-zero. Whose coefficient is non-zero. For example, if you take p of t is 2 plus 3t square plus 5t power 5, then the degree of that polynomial is 5. And if P of t is a naught, that is not equal to 0, the degree of p is 0, is defined as 0. Suppose all these terms vanishes except this one a naught. A naught is non-zero. Then we can say that the degree of p of t is 0. If a naught is also 0, that is p of t is 0, then p is called 0 polynomial. But its degree is not defined. But if it is also a polynomial, it is called 0 polynomial. It is also in our Pn, the set of all vectors of degree at most. So let us define the vector addition and scalar multiplication on the set Pn. If P is given by P of t is equal to a naught plus a1t plus a2t square and so on a n t power n, and qt is another vector by b naught plus b1t plus so on bn t power n. Here the coefficients are changed. Then the sum p plus q is defined by, so we are defining the addition of polynomials here. This is equal to p of t plus q of t. This is nothing but, this is also component wise addition. We are adding the constant term a naught and b naught, and we are adding the coefficient of t, a1 plus b1, and so on. Finally, we are adding the coefficients of t power n. Here it is an plus bn. So in this way, we are defining the addition of polynomials. This is our vector addition group, since our vectors are polynomials. And scalar multiplication Cp of the polynomial is defined by C times P of t. That is, you have to multiply each and every coefficient with C. That is Ca naught, Ca1t plus so on plus Can. So these two are the definitions of scalar multiplication, vector addition and scalar multiplication. With these operations, we can simply see that these two, the first and sixth axiom. First axiom is closed under vector addition. Sixth axiom is closed under scalar multiplication. These two are nothing but the definitions we have given now. So 1 and 6 are satisfied now. Remaining axioms 2, 3. The second axiom is commutative property. Since the real numbers are commutative, here also the vectors, the vector addition is commutative. Polynomial addition is commutative. Associativity also inherited from the real numbers. And 7, 8, 9, 10. These are also satisfies as we are dealing with real numbers. As real numbers hold all these properties, our set Pn also hold these properties. Zero polynomial, that is Pt is 0, is the zero polynomial that acts as the zero vector, which is required under axiom number 4. If you add that zero vector to any vector, you will get the vector added to it. Finally, -1 times p. So that means you are changing the sign of each coefficient. You are multiplying with -1 throughout the polynomial. That means you are changing the signs of the coefficients. So -1 p acts as negative of p. If you add p and -1 times p, all the terms will be cancelled, and finally you will get a 0. So 0 is the zero polynomials here. So fifth axiom is also satisfied. So from these we can conclude that all the 10 axioms are satisfied. Thus Pn, the set of all polynomials of degree at most n, is a vector space. Let us move on to another example. The space of signals. Let S be the space of all doubly infinite sequences of numbers. So it is a sequence of numbers that is infinite on both sides. Let yk be an element of such space where the elements are like this and so on, minus y2, minus y minus 2, y minus 1, y0, y1, y2 and so on. So it is a sequence, infinite sequence. So let us take another element zk in this space S. So we define addition and scalar multiplication. So the sum of two vectors is defined as another sequence yk plus zk. This is nothing but component wise addition. This is also component wise addition. So here you will get y0 plus z0, y1 plus z1, y2 plus z2 as the terms. Here y minus 1 and z minus 1 are added. You will get a new sequence that is the result of these two vectors. Scalar multiple c times yk is the sequence cyk. That is, you are multiplying each and every term of the sequence by c. The vector space axials are verified in the same way as per Rn. So this is also similar to n tuple, but here n is infinite. So component wise addition and component wise multiplication, the operations are similar to the operations in Rn. So all the properties can be proved in a similar manner in which we have proved in the previous example. So these elements of S arise in engineering and wherever signals is present in discrete times. So when the signal is received by us in a fast manner or in a time interval, we can call them as discrete signals. Those values are noted in the sequence, seen in the previous slide. These signals may be electrical signals, mechanical signals, optical signals, and so on. Now signals related issues, you will get a sequence like that. That now we have proved that sequence is the set of all such sequences is a vector space. So you can add the signals and all the theory related to the vector spaces is applicable to that signal space. What we are going to prove, whatever we are going to prove in vector spaces, that is applicable to the signal space. So this space is called space of signals, since it is used for signals. The graph may be visualized like this. The discrete data is pointed here. So we take this as y0. This is y minus 1. This is y minus 2, and so on. This is y10. The value of this one is y. The value of this one is y. So we take all the values of the sequence. This is a vector in our space of signals. So it is a vector space. So the theory which we are going to prove is applicable to the space of signals. The results can be directly used there. And one more example, let us go through one more example, set of arrows. This is used in physical courses, in most of the physical courses. Let E be the set of all arrows. Arrows are nothing but directed line signals. This is a line segment and it has some direction in three-dimensional space with two arrows regarded as equal if they have same length and point in the same direction The two arrows of same length and same direction are equal. So here this is V bar and there is another V bar here. If it is also in the same direction, both are equal, but it is in the opposite direction. So we denote it by minus. So its direction is same, but it is 3 times to this V. The length of this arrow is 3 times to this V. So it is 3V. 3V. So we have to define vector addition and scalar multiplication on this set. So we use parallelogram to define vector addition in this set. So this is the parallelogram law. If this is U bar and this is V bar, you can construct a parallelogram by drawing a vector which is parallel to this one joining here. And similarly, we can draw another vector which is parallel to U bar joining V bar here. The point where these two lines coincide is this one, the position vector of this one. So the point, this is the point, and the line segment joining the origin to this point is the position vector of U bar and V bar. That is the resultant vector. That is regarded as U plus V in our definition. So this is our definition. Wherever you come across two vectors, by using parallelogram, you will get U plus V. This is our definition for this set for vector addition. And for scalar multiplication, we take for each V in V, define CV to the arrow whose length is mod C times the length of V. So if you are multiplying with 5, the resultant vector must be 5 times to the original vector. 5 times to the original vector. If you want minus 5 times V, then also the length must be 5 times to the mod 5, mod minus 5, that is 5 times to the original vector, but its direction must be in the opposite direction. So its direction is in the opposite direction. So if C is positive, just multiply with the scalar. If C is negative, then multiply with the modulus of the scalar and the direction will be in the opposite direction. So this is the way we have defined this scalar multiplication. With these two operations, we can prove that our set V is a vector space. So the definitions of V are geometric and using the concepts of length and direction. So here we have to find a zero vector, an arrow with zero length. That is nothing but a point that represents the zero vector, and that is our zero vector in the vector space. The negative of V is minus 1 times V, that is in the negative direction. Same size, same length, but the direction is in the opposite direction. So the axioms 1, One is evident from parallelogram law. 5 is 0 vector. 4 is 0 vector. Axiom number 4 is 0 vector. 5 is negative of V. 6 is scalar multiple. That is again another arrow, directed line segment. And 10 is 1 into V is V. These are all evident. The remaining axioms can be verified geometrically, like this one. So for commutative property, U plus V. So this is U and this is V. U and V by parallelogram law, by addition, you can get this is our U plus. Similarly, if you add V plus U, you will get this one. Both U plus V and V plus U have same length and same direction. So these two are regarded as equal vectors as per our definition. So U plus V is equal to V plus. Similarly, associative law can also be true. U plus V, this is U and V and W. So U plus V is this one. By adding U plus V and W by using parallelogram, this is U plus V plus W. And this is U and this is V plus W. By adding these two by using parallelogram, you will get the same vector U plus V plus W. So by geometrically observing, can prove all the rest of the axioms. So we can conclude that V is a vector space. So this space is a common model in many physical problems of various forces, magnetic force, electric force, and all such problems. Wherever some force, gravitational force, wherever some forces are applied, this model can be used. We have already proved that this is a vector space. So the theorems which we are going to prove, or the theory which we are going to construct on this platform, is also applicable to the all such forces, applicable to the set V with the vectors of all such forces. So thank you for watching. Let us meet